All right, I like chapter 4. We're about to start chapter 4. Chapter 4 feels like a little bit of a breath of fresh air after all the things that we've been doing in chapters, especially 2 and 3. And so we're going to take a look at section 4.1 today, which is called Antiderivatives. So antiderivatives is the reverse of derivatives. So in very much the same way that multiplication and division are reciprocal operations, right? They're inverse operations. Addition and subtraction are inverse operations. Derivatives and antiderivatives are inverse operations. So the first thing I'd like for you to do is to write down all the derivative rules that you know, which you know them all, so just write them down. So you've got the constant rule, the linear function rule, the constant multiplier rule, sum difference, power, and then your trig rules. Okay, so I want you to write all of those down. And I'm going to push pause while you do that. Okay, if you're still writing something down, it's okay. We're going to fill them all in together. So what's the constant rule? What's the derivative of y equal b?
0.
Yep, y prime is 0. How about the derivative of ax plus b? Close.
1.
A. It's the linear rule, so it's the coefficient of x, which is a. What's the derivative when you have a k multiplied by something? What happens to the k? It's not a product rule because k is not a variable. It's a constant multiplier rule. So what happens to a number in front of something we're taking derivative of? It just stays, right? I like to say it comes along for the ride. And then whatever the f of x is, the derivative of it would happen next. So that's f prime of x. How about sum and differences? What do you do? Yeah, so you just do them independently. And then whatever sign is between them, you put the same sign. So this says plus or minus, so I'll write plus or minus. All right, how about the power rule? What's the derivative of x to the n?
N x to the power n minus 1.
Good. Okay, so everybody good with those? Been working with those for maybe 4 to 6 weeks at this point, at least. Okay, then we have our trig rules. So what's the derivative of sine? Cosine. What is the derivative of cosine? Negative sine. Okay, how about tangent? Secant squared. Cotangent? No, secant's next. Sorry, secant.
Cosecant squared.
Nope. Good guess. That's one of them. Yeah, we're on secant though. Secant tangent. So the derivative of secant x is secant x tangent x. All right, cotangent, which is what I mistakenly said, is which one, Levi?
It's cosecant squared.
Yeah, it's actually negative cosecant squared. So remember the negative. So anytime we have a co-derivative, a derivative of a co-function like cosine and cotangent, so far we've got negatives. And we will for cosecant as well. It'll be a negative. Negative what? Cosecant x, cotangent x. Okay, everybody's good with those, right? Been working on those for a while. So here's what we're going to do. We're going to be taking things that look like what's on the right-hand side of this list and on the right-hand side of this list, and we're going to be going to the left-hand side, or just going backwards. Okay? Now, one thing you might notice as we do that is that this doesn't include, especially my trig functions, all the different trig functions. Like, there's no just secant x on the right-hand side here, correct? Okay? We'll get to that, but it's not in this section. All right? So we will eventually have an antiderivative form for secant x, for tangent x, for cosecant x and cotangent x, but that's not here yet. This section is literally just moving backwards on everything. So we're going to take these different rules and we're going to go backwards in our minds of what happened. How in the world did I get a derivative that was 0? How in the world did I get a derivative that was k? Okay? Now we need a little notation because over here you notice we have y in our left-hand column and then we have y prime in our right-hand column. Well, if I'm now starting with y, I can't put a prime on it. That's the wrong notation. It's exactly the opposite of what I want. I need something else. So the notation that's used is capitals. Okay? So if you start with something that is f of x, then its antiderivative is capital F of x. Okay, all of these say y, so we're going to use capital Y. That's just notation. All right, so how in the world do I get a derivative that's 0? When did that happen? When I had a constant. So this is y equals some constant, and actually we use c when we're doing it. There's nothing special about it, but that's just the notation that everybody uses, a c. C for constant. Is this constant? How do I get a derivative that's actually a constant? How did that happen? Look back at your other list if you need to. Constant multiplied by x, right? It was a linear rule. So that constant, which is called k here, is multiplied by x. But look back at that list. It didn't just say y equal ax. What did it say originally? It said plus b, right? Because what happens is on all of these, there's the ability that there's a constant on the end, because if I take the derivative of a constant, I get 0 and it disappears. So if you imagine going from the right-hand side to the left-hand side here backward, and I took the derivative, the plus c goes away every time. So every time you take an antiderivative, all of this list and every time on your gateway, you're going to write plus c on the end. Okay? Plus c on the end. So what do you suppose happens when you have a constant multiplied by f of x? What happened when you did the derivative? It stayed. And when we do the antiderivative, it will also stay. Okay, so it stays in either direction. None of those, it doesn't change. What's going to happen to the lowercase f of x here? It's going to be an uppercase f of x. Exactly. What do you suppose is going to happen with the sums and differences? We did them independently when we did derivatives, right? We just did them one at a time. And we do them the same way when we have antiderivatives. I need a plus c on the one before. Sorry, left that off. So I need to take the antiderivative of lowercase f of x, which would be the uppercase one, right? It's just notation. I have a plus or a minus, and then what will come next? Yep, the capital G of x. And then I need plus c on the end. All right, this is the most interesting one so far. All of those are really boring. They just feel like I just sort of reversed everything very simply. This one's the most interesting. Let's think about what happens to our power rule over here. The coefficient, the exponent, n, becomes the coefficient, right? And then we decrease the exponent by 1. Now, when it becomes the coefficient, it's a multiplication factor, correct? So I multiply by the original exponent. So over here, what I do is that instead of decreasing my exponent, the reverse or the opposite of that would be increasing my exponent, yeah? So I'm going to increase my exponent. Instead of multiplying, right, I multiplied by n, I'm going to divide. And instead of multiplying by the original exponent, I'm going to divide by my new exponent. Now my plus c on the end, and I want to push pause. So ignore, well, the plus c is 0. But if I were to take the derivative of this, what would happen? Well, the n plus 1 would come to the front, which would then cancel with the n plus 1 in the denominator. The exponent would decrease by 1, which changes n plus 1 back to n, and that's where I started. Do you see it? Right? The exponent, if I were to take the derivative, n plus 1 comes to the front, cancels with the denominator, decreases by 1 to give me x to the n. Okay. And then we have our trig ones. So in our trig ones, we're reversing everything again. So we have to be, probably the most careful we have to be is about signs, because the signs will trip us up if we're not careful. So I have sine. So whose derivative is sine? Cosine. But if I were to take I have a plus c. If I were to take the derivative of cosine, what would I get? I'd get negative sine, which means there has to be a negative here to make this work. I know I've said this before, but I think it's probably worth mentioning again, that the only one I remember is that the derivative of sine is cosine. I mean, like legitimately. And everything else, I just think through when I need to do it. If I remember the derivative of sine is cosine, then the other one's going to be the negative. It means that if I want to take the derivative of this cosine, it's going to have to switch signs. So in order for it to switch signs and get me back to a positive sign, it has to be negative. I don't memorize them because if I memorize them, I'm going to have to memorize them specifically for derivatives and specifically for antiderivatives and keep those all four straight in my head. I don't want to do that. I'd rather just think about one of them and then reason it each time so that I make sure that I get it right. But it's your choice on what you want to do about that. Whose derivative is cosine? Well, it's sine to start with, right? So we have sine, and we have our plus c. So let's think about it again. What's the derivative of sine? It's cosine. So I don't need a negative on this one. Right? The derivative of sine is cosine if I'm going back the other direction. Whose derivative is secant squared? Yep, tangent. All right, what is the derivative of tangent? Secant squared. There's no cos involved here, right? So I don't have any negatives involved. Whose derivative is secant tangent? Secant. Again, there's no co-functions involved, so it's also a positive. Whose derivative is cosecant squared? Cotangent. And is there a co involved here? Yes, there is. So the derivative of cotangent, if I were to go the other way, would actually be negative cosecant squared. There's not a negative on my cosecant squared here, so I need another negative to balance it out over here. Last one. Whose derivative is cosecant x, cotangent x? Cosecant x. And I need a negative for the same reason as before. The derivative of cosecant x is negative cosecant cotangent. There's not a negative in my cosecant cotangent here, so I need a negative over here. Okay, so you've got this list of rules, and you've basically got a week to make sure that you can work through them effectively. So we're going to practice working through things effectively. Do remember on a gateway, you don't have to simplify anything. But as we do homework problems, test preparation, those things like that, not gateway stuff, we will be simplifying as we go. So we've got examples left. Okay, so notation. I haven't talked about notation yet. Whoops, sorry about that. The notation that you're seeing happening at the beginning here and at the end are kind of like bookends, you know, like a beginning parenthesis and an ending parenthesis. They go together. Okay? The script S at the beginning is called an integral symbol. Integral and antiderivative are interchangeable, and you'll hear me say them interchangeably. Okay? Integral, antiderivative, that's that script S at the end, at the beginning. The dx at the end is not going to have a lot of meaning for most of you. But if you take physics, or if you take Calc 4, it begins to have meaning. So let me just tell you what the meaning is so you can see why it's there. Some of you are smiling at each other. It's good. The dx at the end tells you with respect to x. It's simply saying x is my variable. And you're looking at it and thinking, well, duh, x is the variable. What else would it be? Well, when you get into physics and differential equations in Calc 4, you have what are called multivariable functions. So you have functions that have x's and y's and z's and maybe other letters, whatever, all involved in the same in-between part, right? The integrand, the part that's in between. And so you have to know which one right now that you're considering as the variable. That's why it's there, okay? For the purposes of what we're doing, we can think of it like bookends. We have the script S at the beginning, the dx at the end. They're either both there or they're neither one there. So when there's one present, there's the other one present. When I remove one, I remove the other. Okay? They're bookends. So in between, right here, is what I'm working with. 2x. what would I have had to take, I'll do it a couple different ways to think about it. What would I have had to take the derivative of to get 2x as the derivative?
X squared.
X squared, okay? So we can think of it that way, x squared. Or you can think of it like this. This is 2x to the 1. It is. I increase, the 2 at the beginning stays. I increase the exponent by 1. That makes it a 2. And then I divide by my new exponent, the 2. And then, of course, the 2's cancel out. So there's two different ways to think about it. They give us the same answer. They're definitely the same process, just from a different perspective. Let's do the same thing, since I just presented that idea, with the 3x squared. So the 3 stays because it's a constant multiplier. If I increase x squared's exponent by 1, it becomes x cubed. And I divide by my new exponent, which cancels out my 3's. I'm not finished. The other perspective for the 3x squared is I could say, what would I have taken the derivative of to get 3x squared? And the answer is x cubed. So either of those are fine. This one's actually really nice because it said 3x cubed and not like 8x cubed, right? So this perspective down here tends to work generally a little bit better because we don't always have the coefficient that's very obviously the number that came down when I took a derivative, right? But I need one more thing. I need a plus c. Thank you, Levi. I need a plus c. Every time I take the derivative here, I need I need a plus c. How could I check to make sure that this is right? I could do the reverse. I could take the derivative of this, right? Every single time you can check your work. You can do it on the gateway easily as well. Every time. So if I were to take this derivative, the derivative of x squared is 2x, that checks. The derivative of negative x cubed is negative 3x squared, that checks. And the derivative of the plus c is 0. Okay? The benefit to the antiderivative gateway versus the derivative gateway is that we have far fewer rules. Notice what you don't have. Product rule, quotient rule, and the chain rule. And there's a very good reason you don't have them. Because there's an entire chapter plus, maybe, I think it's just an entire chapter in Calc 2, for those of you who are taking Calc 2, devoted to what happens when I do have a product. What do I do? What happens if I do have a quotient? What do I do? And it's not near as easy as it was, and you also didn't think it was easy, but it's not near as straightforward anyway as it was when you do derivatives. It's complicated. Okay, it's very complicated. It's chapter, I can't remember. I think it's chapter 5 of our book. It's integration techniques, and it's complicated, right? So we don't do that in Calc 1. That's not part of our curriculum for this. It's just not. So if anything does look like it has a denominator, what that means is that there must be some way to simplify it with algebra to use all the rules that you've established so far. So the first thing I'm going to do on number 2 is to rewrite this in a different way. How can I rewrite 1 over x to the 6th? Right. This is x to the negative 6th, and then I have my minus 2 dx. Now this looks like a power rule, right? And I can use the power rule. Please be careful with negatives with the power rule, because people sometimes get tripped up with adding and subtracting, just like you did when you were taking derivatives. We sometimes sort of think about like numbers going down in value or up in value, but remember, really it is subtraction and addition. Negatives kind of work the opposite of our intuition with positives, right? So if you need to actually write it out, I'll do it this time. Do so. I'm adding 1, and then I'm dividing by negative 6 plus 1. You can leave it like that on a gateway. You're not going to leave it like that in general, though, right? Please don't, right? That's first grade stuff at this. Well, it's not because it's negatives. How about 7th grade anyway? It's 7th grade because it's got negatives in there. Okay, and then what do I do with the 2? It's 2x. Anytime you have a constant, we attach an x to it because the derivative of 2x is 2. Okay? What else do I still need? Plus c. On a gateway, you stop right there. But for the purposes of what we're doing, if it starts out with no negative exponents, it needs to end with no negative exponents. So I need to do a little bit of cleanup. Negative 6 plus 1 is negative 5. So I'm going to do cleanup in 2 steps. Feel free to do it in 1 if you wish. X to the negative 5 over negative 5. My exponent is still negative, so I'm going to take my x to the negative 5 and I'm going to move it down in the denominator. The negative 5 that's there stays. So now I have 1's on top. The negative 5 is still down there. I have x to the 5th down there as well. Oops, minus my 2x plus my c.
So we don't have to figure out what plus c is, we just put plus c?
That's a really good question, Lauren. For the purposes of gateway, no. In general, no. You need additional information to figure out what the plus c is. And we will get it in one section where you'll probably be asked to do like one problem on a test, a couple problems on a homework. It's not complicated, it's just not enough information given right now to figure it out. Okay, so let's actually talk about why the plus c is happening though. So think about what happens when you have a function. If finding the derivative is associated with finding slope, right? It's the slope. How's the graph shaped? If I were to have, and I'll draw a picture you're familiar with. What is this a graph of? Approximately. Parabola, y equal x squared, right? If I have this graph, or I have, again, these are not drawn well. Pretend like it's the same thing shifted up. It's identical, right? Pretend. The slope's the same everywhere, right? This right here is the plus c value that we're talking about. If I just shift it up, it doesn't change the slope. That's why the plus c happens. So if I take this graph and I take the derivative, I get the exact same derivative because the location in space shifted up and down is irrelevant. That's why the plus c happens. So what we need in order to actually figure out what the c is, Lauren, is we'd need an additional point given to us. We'd need to know a location on our graph, and we're not given that on these. Yep.
Why didn't we put the negative 6 plus 1 in front of it to cancel out like we do elsewhere?
So take a look over here. The power rule is division.
Okay.
You're thinking about the power rule with derivatives, which is the multiplication part.
Okay.
So we're dividing by our new exponent, not multiplying by our previous exponent. Yep.
Got it.
It's an adjustment. I understand. Okay, this one looks like it's got division in it as well. At least it's got a denominator. And it's got a radical. Thoughts? How can we change this into something we can work with?
To the top, so x to the negative 1 times x to the negative 1.
Okay, so I'm going to go with what Lauren just said, because that works. If the x is in the denominator, I can move it to the top and make it x to the negative 1. I'm not going to have anything in the denominator next, so I'm just going to write it as though it's the piece itself. I don't need a denominator. And then the other one, the x to the, or the square root of x in the denominator is moved to the top. So it's 1/2 in the denominator. That's what square root of x is, right? But it's in the denominator, so it's negative, so it moves up, and it's also going to be, it's in the denominator, so when it moves up, it's going to be negative. There's my bookend dx. Okay, now that's better. I don't have a denominator, and I don't have radicals. But there's one more step of simplification I need to do, because right now it looks like a product. I don't have a product rule. So what am I going to have to do before I actually take an antiderivative here? I'm going to have to combine them. Yeah? So I've got x to the negative 1, and I've got x to the negative 1/2. These are exponent rules. Okay, so that's algebra 1. What's your exponent rules say that you need to do with those exponents if we're going to combine these two pieces together? You're going to add them. So negative 1 and negative 1/2 would be negative 1 1/2. which is not a very nice way to write things, at least for what we're going to do. Negative 3/2 is better. So you can add the -1 and the -1/2 to get -3/2. Okay, so far we haven't done any calculus. It was all algebra. Now we're ready for the calculus. What are we going to do with x to the -3/2? And add 1. Okay, so I need to take -3/2, add 1, and then divide by the -3/2 plus 1. Plus c on the end. What is -3/2 plus 1? -1/2. Yep, and we're going to get a square root in a minute here. So this is x to the -1/2. I've still got division by a -1/2 fraction, which is not very nice. And I have plus c. Okay, so in terms of where do I stop for the gateway, you stop here for the gateway, right? Or if you've done the addition in your head, that's fine too, and you can stop here. That's fine too. But in terms of finishing this up to look nice, the problem started out with no exponents at all. It had radicals. And there certainly weren't negative. So I need no negative exponents, no exponents that are fractions. I need both those pieces to be eliminated. And I can't have division by a fraction in a simplified version either. That's like a big no-no. So let's deal with the negative exponent part first, because we've already talked about it. What do I do to make that exponent not negative? Bring it to the denominator. And how do I get it to be not a 1/2 when I do that? Square root. Okay, so my next step, hang on, I'm going to do this. Give myself a little more space. Okay, so we're going to put, it'll be a 1 on top for the moment. I have a -1/2 in the denominator, and now I have a square root of x in the denominator. So that's one issue we dealt with. Second issue is the -1/2 in the denominator. What do I do so I don't have a -1/2 in the denominator? Close, not the word you want. Reciprocal is the word you want. Yeah. So we want to multiply by the reciprocal. So if you think about it, let me shift it over so I can multiply. If I don't want this in the denominator, I would multiply by its reciprocal to move it. And I'll multiply by the negative as well, just so that I can move the negative up. If you don't multiply by the negative, it's fine. It won't hurt anything. But the reciprocal of -1/2 would be -2/1. And the reason I like that, or we would want to use it, I should say, is because those cancel out to give you the number 1. And then I have only square root of x in the denominator. But in the numerator, I've got -2/1, which is the same as -2, being multiplied by the 1 that's there. So now I have a -2 on top. And when I look at that, and I look at the original problem I was given, they look alike. And that's our real goal at the end, is that they should look like the same form. And they do. So we are done with this one in terms of simplification. Well, what about number 4? Looks like a product. You foil it, right? So this is what my 9th graders are working on right now, foiling. We're going to foil it, no biggie. So remember, on the front end of all these things, if anything looks like multiplication or division, there's some kind of algebra from your past that you can do, and that's what you need to do next. So let's foil this out. So if I were to foil this, first, outer, inner, and last, I have 3x squared. The outer terms is 2x, and the inner terms is, negative. The outer is -2x, the inner is positive 3x, so this is giving me an x, and then the last term is -2. Okay, everybody good with that? Now it's in a form that we can work with very nicely. So 3x squared, what's the antiderivative of 3x squared?
X.
It is x cubed. Feel free to do it in a couple of steps if you need. What do I do with the plus x? Okay, so it is x to the 1. So if you're not thinking of it that way, that is correct. It is x to the 1. So it becomes x squared, and then we divide by the new exponent 2. And how about the -2 at the end? negative 2x. Thank you, plus c. And we're done. If you don't want to write it as over 2, you could write it as a fraction 1/2 in front of it. It's not any different, and it's not any better. It's just another option. But we're done.
So on this one for Gateway and for Oklahoma, we could stop there.
Yes, yeah, it's the same stop spot on this one. That will happen sometimes. On this one, if it had not said 3x squared here, like it said something else like 4x squared, your antiderivative gateway might actually look a little different than the final version here. This one's final version is really nice. You also could have it written as 3x cubed over 3 on your antiderivative gateway if you're thinking about it from the perspective of, oh, look, I need to increase the power by 1 and divide by the new power. So that would be another version that would be okay. Okay? All right. We're going to do a few with trig. Okay, so number 5 has 1 and negative cosecant x cotangent x. So the 1 part is clearly not trig, right? It's just the algebra stuff we've been doing. What is the antiderivative of 1? X. Derivative is 0, the antiderivative is x. You're going to want to keep going back and forth, so just be careful. Okay, it is x. So what about cosecant x cotangent x? Okay, so the derivative of cosecant cotangent is cosecant. And it's a cofunction. That's what's generating that negative, right? So the derivative of cosecant is negative cosecant cotangent, which is what I have, negative cosecant cotangent. So it's plus the cosecant x and then plus c. And as much as you may feel like trig's not your thing, that's the easiest we've done so far. There's no simplification. I mean, there's no numbers moving around or anything like that. It's a very clean one. 6 is not a very clean one. We cannot take this at face value and just move with it like the last one. We do have something that looks like division. Okay, so if you have not already done so, which you should have because I've said this like 5 times, but I'd print out the trig identities that are posted in Canvas. One of the trig identities sets is called Pythagorean identities. Okay? Pythagorean identities are the ones that show some squareds in them. You've got sine squared, you've got cosine squared, there's some secants and some cosecants squared, things like that, okay? So tangents and cotangents as well. So the denominator here is a version of one of the Pythagorean identities. The version that it is that sine squared of x plus cosine squared of x is equal to 1. Now, I know that there doesn't appear to be anything in the denominator that says cosine squared. I understand that. But what that means is that this sine squared bit over here just needs to move to the other side, and then it will look like this. So if I subtract sine squared to the other side, I will have 1 minus the sine squared of x. And that's what I have in the denominator. This is exactly my denominator, right? So what that means is that I can replace the denominator with cosine squared. Now, it might not be clear to you right now why that's preferable, but the reason that it's preferable is because there's no addition and subtraction down there now. Okay? Eliminating addition and subtraction in denominators makes things easier. And the reason it makes things easier is because when I divide by the denominator, I actually have addition and subtraction that has to go with each piece of a numerator. I don't have addition and subtraction to deal with now. So watch what I'm able to do. This is sine x, and I can break this apart to say cosine of x, cosine of x. So far, so good. That's what cosine squared means. So I can rewrite this as the numerator 1 over cosine of x and the numerator sine over cosine of x. So I'm using properties of fractions, sort of the reverse of what we normally do. But it's very clever. And the reason it's very clever is because each of these pieces is now another identity on that sheet. What is 1 over cosine? Secant. And what is sine over cosine? Tangent. Now there's no more denominators. And now it looks like something I already have an antiderivative form for. What is the antiderivative of secant x tangent x? It's just secant x. Yes, plus c. Y'all are doing a good job on the plus c's today. But there were 3 different trig properties that took to get to there. You have to know your trig properties in order to work with this problem, right? You just do. Okay. Oh, do you see what's happening next, Lauren?
Yeah.
Yes, this is Lauren's question. So let me pause right quick and just say, everything on the gateway looks like these, problems 1 through 6. Okay, without the simplification that we did at the end. Okay, it's everything 1 through 6. 7 and 8 are not gateway questions, all right? But they're the ones that Lauren was asking about. Do we have to figure out what C is? And for 7 and 8, you do. The red flag phrase is particular. It is a particular solution. What we've been finding so far was a general antiderivative, because it had the plus C on the end. It was in general. These are particular. So what we're going to do is we're given f prime of x is equal to 4x squared. Notice they've written it in prime notation, f prime. So when I take the antiderivative f prime, I don't need a capital F. I just need to remove the prime. Are you with me? So as I'm writing this down, I'm going to take the antiderivative of this. My space is not great here. The left side is just going to be f of x. 4x squared. Okay, so what's the antiderivative of 4x squared? Well, the 4 stays. And then what? X to the third over 3. Plus c. This is my general form. This is a general antiderivative, okay? The particular solution part means I take the information given at the end, f of negative 1 equals 3, and I evaluate it. So I put in negative 1 for all my x's. And then f of negative 1, it said was 3, so I have a 3 on the left. So you could, actually, let me just write it over here. Okay, so it's 3 on the left, and then I've got my negative 1s and the x's on the right. Good? We're just doing an evaluation step. Again, we're back to an earlier algebra kind of concepts you've worked with. What is negative 1 cubed? Negative 1 times 4. So I have negative 4 thirds on the right, plus c, and I have 3 on the left. And then what do? I add the 4 thirds. So what is 3 plus 4 thirds? Let's try it as a mix, or as a whole number. That's not the words I wanted still. An improper fraction is what I meant to say.
7/3.
So it's not 7 thirds. It'd be 13 thirds. So where did the 13 come from? Okay, so this is 3 over 1. So in order to add fractions together, we have to have like denominators. So if I multiply this denominator by 3, it will match. So in the numerator here, I have 3 times 3. There's my 9. 9 plus my 4, that would be 13. 13 over 3. If you write it in a mixed number, it's okay. You could do that. It'd be 4 1/3. You could do that. It's kind of not the way we normally see it written, but it's okay. You can't change this one into a decimal because you'd get a repeating decimal, and we definitely are not going to write repeating decimal forms on things. That's not going to work. Now, this found C, that didn't answer the question. The question said to find the particular solution. So we take the original solution that we had found, f of x equals 4x cubed over 3, and we replace the c with what we found that c equaled, which is 13 thirds. This is the particular solution. And again, you could check it by taking the derivative and finding that the derivative is going to be equal to 4x squared. Sorry, 4x squared. Okay, let me work through number 8 really quickly before we run out of time. This one is quite similar, except that it starts with the second derivative. It just means I'm going to do the antiderivative twice. That's all it means. So I'm going to start with finding the antiderivative here. So this will give me an f prime of x on the left. X squared becomes x cubed over 3 and plus my c. The notation for f prime says that I have to be given two initial conditions to make this work. So f prime of 0 is 8. So I replace the f prime with 8 on the left and the x with 0 on the right. What will c equal? 8. Yeah. So my function is now f prime of x equals x cubed over 3 plus 8. But I have to do it a second time. I'm trying to find the original function. So I'll take it one more time. So on the left, I will get f of x. On the right, x cubed becomes x to the 4th. I'm going to divide by 4, but I've already divided by 3, so 4 times 3 is 12. There's a 4 times 3 in that denominator now. The 8 will become 8x, and then I have plus c. The last piece I was given was that f of 0 is 4. So I put 4 in on the left, I put 0 in on the right. What will c equal in this case? This is a second c value. Let me call it c2 because it's not the same c. It's not going to equal 8. It certainly would have to. What will this c value equal? 4. So my particular solution is f of x equals x to the 4th over 12 plus 8x plus 4.